Good afternoon, D Block. You need to go ahead and get out your stoichiometry handout, which you should have. You can put this in your notebook afterwards. Grab out your periodic table. You will need a calculator and a pen or pencil. We're going to start on this handout with the side that says examples and then says number 1. So I'm going to teach you with every problem how you can use this map. The very first step when we're tackling a stoichiometry problem is that we need to have a balanced chemical equation. So for the examples that we are going to be using today, 1 through 4 on the back, our chemical equation is not given to us, but I'm going to give that to us. The ones that you're going to have in your packet, you will have the equation. It just might not be balanced. So that's our first step. Step number 2 is identify your known and unknown values. And more specifically, where are you on this map? So you're going to see that you've got the left side is your known, the right side is your unknown. So when we're going to read the problems, we're going to figure out where on this side am I? Am I starting out at liters, grams, mole, or particles? So we're going to determine where we are. And then for our unknown, that is what is our problem asking us to find. And we're going to see on which side which part of this side are we on. And then we are going to determine the ratio from the coefficients, just like we did yesterday with our graham cracker stoichiometry lab. And then we're going to determine the path to the answer. So where are we? Where are we going? How many steps is that going to take? And we're always moving from known to the unknown. So we're always going to start somewhere on this side and move over to the right-hand side. And like I told you all yesterday, you have already done the bulk of the work for stoichiometry because you already know, and I'll write these here, 1 mole equals 22.4 liters of a gas at STP. And all of our calculations are going to be at standard temperature and pressure. We also know that 1 mole is equal to the molar mass in grams. And then the last one goes between mole and particles, which remember that's atoms, molecules, or formula units. So 1 mole equals 6.02 times 10 to the 23rd particles. So this is what we learned in our mole unit. What we learned yesterday from our lab is that we can use those coefficients to represent a ratio. So we used that in our lab to figure out if we had a certain number of graham crackers, how many s'mores could we make? And that came from a balanced equation. So that's always our first step, and you're going to hear me highlighting that several times. So we are going to jump in. I'm going to draw the map next to each problem. Okay, so our first problem is how many mole of oxygen is produced when 1.5 mole of water decomposes. So we need our equation first, and I'm going to leave myself some space here for us to do it. So when water decomposes, it will break down into hydrogen and oxygen, but you and I know those are part of Brinkelhoff, so they are diatomic. Step number 1, it has to be balanced. So we can't even do our actual problem until we balance this. So I have 2 hydrogen on my reactant side, 2 on my product side. I have 1 oxygen on my reactant side, 2 on my product side. So to fix that, I'm going to place a coefficient of a 2 here, and now I'm going to have 4 hydrogen, 2 oxygen. So my oxygen numbers are good, but hydrogen, I only have 2 here on the product side, and I have 2 times 2, so 4 on the reactant side. So I'm going to put a coefficient of 2 here. 2 times 2 is 4. And remember, when there's no number, it's not a 0, it's an understood 1. So just like our lab yesterday, you need 2 graham crackers for every 1 marshmallow and 4 chocolate pieces to get 1 s'more. Okay, now we can do our problem. All right, our unknown is the mole of oxygen. That's what we are asked for. Our known is going to be 1.5 mole of water. So our steps are figure out where on this side of the known map are you, where are you going on the unknown side. So I'm going to draw my map out to the side. PMLG, I'm going to abbreviate MPLG. All right, on my known side, I am given mole, so I am here. On my unknown side, so what I'm trying to find is the mole of oxygen. So on the unknown side, I am here. And we have our conversion factors that help us go in between here. But if we want to go from mole of one thing, our known, to mole of our unknown, we need our ratio. So we're going to use those coefficients. It's also called a mole ratio, but we can just call it a regular, just a ratio like we did yesterday. So here's how our problem starts. It's going to be only a one-step problem. We're going to start with our known, 1.5 mole. In stoichiometry, it's going to be important now that we actually use the formulas. We are starting with not just 1.5 mole, but 1.5 mole of water. So we have to write in that H2O piece. It's only one step, so we're going to set up for one step. Our unknown, what we want in the end is we want the mole of oxygen. So now, on this part, we are going to use our ratio, and that comes from our coefficients. And we only need the coefficients of our known and our unknown. Right, so I've got water here. I need oxygen. So I'm going to find their coefficients from the balanced equation. I want to get rid of water, so I need to have water on the bottom. I want oxygen, so that has to be on top. For this part, I'm going to find what the coefficients are from the equation. 2 is going to go in front of H2O, and 1 is going to go in front of O2. My waters will cancel, and now it becomes a normal problem. 1.5 times 1 is 1.5. Divide that by 2 on the bottom, so I'm going to simplify this into, so type it in my calculator, 1.5 divided by 2 is 0.75 mole of oxygen. Okay, let's move on to number 2. Draw my map like I did before. So number 2 deals with the same equation as before. I did that on purpose, that way we wouldn't have to keep writing equations over and over. Okay, so I've got my map. First step, balanced equation, done. Step number 2, identify your known and your unknown values and figure out where they are. So your known always starts out somewhere on this side. Your unknown is on the other side. Okay, so let's read through our problem. How many mole of hydrogen is needed to react with 0.5 mole of oxygen? So our known is 0.5 mole of oxygen. So here is our known side. We are given mole. We want to know how many mole of hydrogen do we need. So M stands for mole. So like number 1, this is a one-step problem. So we will start the same way we did before. 0.5 mole of oxygen. So we have to now be specific. We're going to set up for one-step problem because that's all it is, one jump. We want mole of hydrogen. So we write that as our game plan to help us. So that means we should have hydrogen up here if that's what you want, and oxygen on the bottom so they cancel out. So here's our balanced equation. We're going to put, for every 1 oxygen, we need 2 hydrogen molecules. So for every 2 hydrogen molecules, there is going to be 1 oxygen molecule. Oxygens are going to cancel out, 1 on top, 1 on bottom. Multiply the top numbers and then divide by the bottom. So 0.5 times 2 is 1. Our bottom number is just 1. So 1 divided by 1 is 1. Woo! Look at us doing that tough math. Go D block. So 1 mole of hydrogen. 2 more problems. All right, so flip over onto the back side. I don't have the steps listed here, but they are the same. We're still going to draw our maps out to the side, and I still have the big map up top. How many mole of hydrogen is produced when 64 grams of water decomposes? So I'm going to draw my map. All right, I'm going to go back and read the problem. And again, we are using the same reaction as we did on the front page that we already balanced. Okay. Our known from the problem is 64 grams of water. So again, be specific with what substance is it. 64 grams of water. Our unknown, what we're trying to find, is mole of hydrogen. So in terms of using my map, on the known side, and we're always going left to right, I am at grams. On the unknown side, I am trying to find the number of mole of hydrogen. Okay, and as we notice, there is nothing that connects those two, so this is going to take us 2 steps to do. So from that, you can see the biggest problem would be only 3 steps. So we're only adding in that additional step. So we need to go from grams of our known, which is water. We need to figure out how many mole we have, and then we need to go to mole of hydrogen. So it's going to take 2 steps, so let's set up for that. 64 grams of, write the formula, H2O. Do not just write 64. Do not just write 64 grams. You have to say 64 grams of water. And it's going to take us 2 steps. So I leave space for that. If I use my map, there's no guessing. What we want is our unknown, and it's mole of hydrogen. So I'm going to set this over here. And as a reminder from the front page, in case we need these, here are our constants for everything that a mole of a substance equals to. So at standard temperature and pressure, it's 22.4 liters. It is always equal to the molar mass in grams of your substance. Remember, we have to find that number always. And then it is equal to Avogadro's number, or 6.02 times 10 to the 23rd. And that is particles, so tiny items, atoms, formula units, or molecules. Okay, just like before, whatever you are starting with, get rid of it. So if we are starting with grams of water, We need to have grams on the bottom. We'll have to use this conversion factor. It's the only one that has the grams in it. So we are stuck. We have to use the other half. These are equal to one another. So I'm going to place grams on the bottom, and I'll put the other half as 1 mole on the top. Remember, you cannot change these. These are constants. So it's always 1 mole equals the other half. All right, here we're going to need the molar mass of water. So we've got to figure that out, because technically we have, in every 1 mole of water, you have a certain number of grams of water. See, now we have to be very specific, because I need grams of water to cancel. So I'm going to look up hydrogen's molar mass, or excuse me, water's molar mass, H2O. We have 2 hydrogens, each with a molar mass of, my periodic table rounds a little bit, so 1.01, plus I only have 1 oxygen, so 1 times, look up oxygen's molar mass, 16.00. Plug it all in my calculator. 2 times 1.01 plus 16 equals 18.02. So that is the number of grams in 1 mole of water. All right. My next problem, next spot, is I'm going to go from, and again, grams of water cancel. Now I have mole of water, and I need to go to mole of hydrogen. Here's where I get to use my ratio of the coefficients. This is where we get to use it, from going from our known to our unknown. So I look at my coefficients. The ratio is that for every 2 water molecules, I will get 2 hydrogen molecules. So I'm going to put 2 H2O on the bottom, and then 2 H2 up top. And again, my numbers are coming from the balanced equation. So my water's going to cancel out, and I do the problem the same way we did before. 64 times 1 times 2, and I am getting 128 divided by all the numbers on the bottom, 18.02 times 2 equals 36.04. I need to simplify this. 128 divided by 36.04, and I am getting 3.55 mole of hydrogen. Okay. Last problem for us. What volume of oxygen is produced when 150 grams of water decomposes? So again, first step is always a balanced chemical equation. We're going to use the same one we used before. I'm just going to jot it down here. Okay, draw my map out to the side. I'm going to figure out my known and unknown values, and then I'll use those to figure out where am I on this side, where am I going here, and how many jumps. Remember, each jump represents a step. So my known is 150 grams of water. My unknown is volume of oxygen, meaning we want liters of oxygen, and this is our unknown. So I'm going to use my map now. I'm starting at grams on my known side, and I am going to liters on my unknown side. Again, nothing connecting these two. So the only way to go from this side over here is we've got to go from our grams of our known to mole of it. Then we can go mole to mole and then do one last step. So I drew 3 jumps, so that's going to be 3 steps. So we'll start by writing our known 150 grams. Write the formula H2O. Again, do not just write 150. Do not just write 150 grams. I need 150 grams of water, and it's going to take me a couple steps to do. So I'm going to set up for each one. Okay, so this is as long as our problems can get. Always write what are you looking for on this side to guide you. So we want liters of oxygen. Don't write just liters. Don't just write oxygen. Write what are you looking for. Okay, so following our map, I need to go from grams of water to mole of it, because I'm still on this known side. And if I'm given grams of water, I need to go to mole of water. So remember also that whatever you're starting with, get rid of it. So if we're starting with grams, it means we're going to have to use this conversion factor. So I'm going to put 1 mole on top of water. On the bottom, I'm going to put grams of water. And we already calculated the molar mass of water in problem number 3. So I'm going to plug in this number here, so 18.02. So my grams of water cancel. So step 1, excuse me, now you can see. Step 1 is done. We went from grams to mole of water. Now we need to bridge this gap between mole of our known to our unknown. So we're going to use our ratio of our coefficients to help us do that. So I need to go to liters of oxygen, but I have to go to mole first. So I'm going to use the ratio. There are 2 hydrogen molecules for every 1 oxygen. My waters are going to cancel. Again, these numbers came from our balanced equation. We never guess. We just know by looking at our balanced equation. All right, the very last step, so we went from grams of water, we found mole of water, or at least plugged it into where that's what we had left. Now we have gone to mole of oxygen. That's the only unit I haven't canceled out yet, but we ultimately want liters of oxygen. So in the end, I need liters here. And I only have one conversion factor that does that. Again, we can't change these, so 1/2 is going to be 1 mole. The other is 22.4 liters. So I'm going to put 22.4 liters up top because that is what I want. I'm going to put 1 mole on the bottom. So my mole cancels out because this is really 1 mole of oxygen. So it all works out. And my only unit left will be liters. So now I'm going to multiply 150 times 1 times 1 times 22.4. And I'm getting 3,360 divided by, multiply all of our bottom numbers. So 18.02 times 2 times 1. 36.04. We're going to divide top by bottom. And I am getting 93.23 liters of oxygen. what I want you to do is try some problems on your own. So you should now be getting out your stoichiometry packet. And I want you to be working on problems 1 through 8, which is on the back of the front page. Before you begin, on numbers 1 and 2, it says given the following equation, and it's already balanced, both of these. Show what the following molar ratios would be. Now, when we did our problems, we said there's 1 oxygen for every 2 water. But you could also call those mole ratios, meaning there's 1 mole of oxygen for every 2 mole of water. I just simplified it. So what this is asking is for you to look up the coefficients from the balance equation. So for example, this first one is blank mole of C4H10 and then blank mole of water. So how many of this do you have for every oxygen molecule? So you're just going to look up the number. So it would be 2, and for oxygen, 13. And no need to reduce these. So just find the numbers from the balanced equation, and you're going to plug them in on numbers 1 and 2. Once you get down to 3 through 5, first step is always to balance the equation. I have given you all of the equations that you need. Some are balanced in this packet, some are not. But as for 1 through 8, none of them are balanced. Do not take up all of this space to balance an equation. That is not the goal. The goal is to be able to do mole problems. So for example, we need to balance this equation first. I would take up a very small amount of space. It has nitrogen and hydrogen on each side. You have 2 nitrogens and 2 hydrogens on your reactant side. The product side, we have 1 nitrogen and 3 hydrogens. So remember, we pick one to fix and we focus on that one first. So I'm going to fix my hydrogens. I have 2 here on the reactant side, and on the right hand side, my product side, I have 1. So I'm going to place a 2 here. That fixes 2 times 1 nitrogen is 2. 2 times 3 hydrogens, though, we now have 6 hydrogens. So to fix on my reactant side, I'm going to place a 3 in front of hydrogen. And remember, when there's no number, it's an understood 1. Now, as for number 3, now is where we need to have our map out to the side. We are asked how many mole of hydrogen are needed to completely react with 2 mole of nitrogen to produce ammonia. All that we need from this problem is to know what is our known, what is our unknown. Our problem gives us 2 mole of nitrogen. The other piece, to produce ammonia, is just referencing the product that's made. We're only ever comparing 2 things at a time, our known and our unknown. So on number 3, we are starting with 2 mole of nitrogen, which remember, nitrogen's diatomic. This is our known. Our unknown, how many mole of hydrogen? As for our map, our known side, we are at 2 mole. So we are at mole. On our unknown side, we are going to mole of hydrogen. So that's just going to be 1 step for us. So start by writing your known. Write everything, including the formula of your substance. So N2. It's only going to be 1 step, so I will set up for 1 step. Our unknown is mole of hydrogen. Now I'm going from mole to mole, I use that ratio. So I'm going to use the coefficients. There is 1 mole of nitrogen. I'm just going to put 1 in 2, but it does mean 1 mole for every 3 mole of hydrogen. So 3 H2. So nitrogens cancel. 3 times 2 is 6 divided by 1. So your answer on number 3 is 6 mole of hydrogen. So you all need to be working on 1 and 2. And again on 1 and 2, copy the coefficients down. And then I want you to keep working until you get to number 8 on here. If you feel comfortable and confident with 1 through 8, you're going to be asked to go and start working on numbers 9 through 13. As always, if you have any questions, you know how to get in contact with me, but I do expect you to be working today. So I expect to see a lot of work done when I come back on Thursday. Be good for the sub, be good, wonderful people that I know that you are, and leave those phones away. Love you all. Bye-bye.